Okay, let's begin. We're continuing where we left off in the earlier lecture 25. So really don't need to do a full recap. What we talked about in the last lecture was the all-pass lattice and its properties. So basically that is what we will start from. We have also introduced some terminology, a bounded transfer function, a bounded real transfer function, lossless transfer function, lossless bounded real, and power complementary transfer function. So again, these are all going to play an important role. The focus of today's this lecture is twofold. One is to bring us to the context of the all-pass decomposition. So this is going to be a key part of today's lecture. In the process, we are going to pick up some useful tools by way of the factorization of polynomials, the property of mth band filters, which is also satisfied by Nyquist filters. So again, revisit something with Nyquist, something with m band. Specifically when m is equal to 2, that becomes, we call it, instead of calling a 2-band filter, we call it a half-band filter. So m equal to 2 is a half-band filter. So this is this is a subset of this. So from general M we go to half band, and that is the last stage before we get to perfect reconstruction for a 2-channel filter bank. Perfect reconstruction, as we have defined it, aliasing is cancelled, no magnitude distortion or phase distortion. Okay, so basically you get exactly the same transfer function back. So that is what we have been trying to achieve, and that is what we will be able to get by the end of today's lecture. Again, if time permits, we go all the way down, or we stop at some point which is reasonable. So let me start with a quick point about lecture 25. So lecture 25, this is what I would like you to carry away from lecture 25. So lecture 25 we saw a lattice. So with this, being able to compute transfer function computation, I think that is an important element. Then what are some of the properties and how do they affect the lower order transfer function Gn minus 1 of z, and how do they carry forward to the higher order transfer function Gn of z. So basically lattice preserves some properties, and then how do we do that. So in our case, the lattice structure did the following. So if I had a causal stable real valued all pass transfer functions, causal stable real valued, you do not have to specify real valued, but most of the time that is what we are interested in, all pass. Then we said that Gn of z can be written using the paraconjugation property, a denominator polynomial Bn of z, z power minus n, the paraconjugate Bn tilde of z. Okay. And in the lattice we enforce the condition that mod Kn, again this is with reference to the lattice, that mod Kn is less than 1. That is because of the stability, to ensure stability. Now if we and of course we also said that Kn will be real valued, we claimed, and this is something that I would like you to validate, show that Gn minus 1 of z, we have more or less done all the steps, but I would like you to go through and show that this is z power n minus 1, it is one order lower than the original polynomial. Bn minus 1 of z is the denominator, the numerator is Bn minus 1 tilde of z. So this is also an all pass, okay, and the claim is that this all pass function is causal, stable, real valued, and real valued meaning by the real valued coefficients. Okay. Now there is a corollary that is written, or that corollary that we can write down, which you should be able to validate and prove, that if you start with G0 equal to 1, that is basically G0 of Z, or whatever you want to call the 0th order all pass. Then if you construct a lattice, any transfer function realized by lattice with the constraint that mod k is less than 1 for all I, however many stages you have, then the overall transfer function Gn of Z is a structurally stable all pass. That means the stability has been enforced by the structure, is a structurally, well, what you can show is it's a stable all pass, but how did it achieve its property? It's because of the structure and the way you construct from the lower order to the higher order, and the property gets preserved. Structurally stable all pass, that is a useful result for us to verify. Okay. Now very quickly let us run through the other concepts and build on that. So we looked at the context of Nyquist filters. These are usually involved in interpolation or decimation. So we made the observation that when you have a Nyquist filter which is used for example interpolation by a factor of m, then we saw that the 0th polyphase component had only one non-zero coefficient. Basically if you view it as a 0 phase filter, okay. So if you view it in the 0 phase form, then that basically means that there is a middle point and then it is symmetric on positive and negative. Of course if you shift it, this will become a delay, but basically one of the polyphase components has got only a single non-zero coefficient, okay. That was an observation that was made. We will build on this in today's lecture. Now what are some of the other things that we talked about? One was boundedness. Bounded basically means that He of j omega is less than or equal to 1 or some constant for all values of omega. That is the property of boundedness, and typically in the context of filters this is very easy for us to visualize. So for example, if I had a low pass filter which had a certain ripple and a stop band, okay, it had a ripple of this type. I am just showing it with equiripple for illustrative purposes, okay. If this line is 1, then the upper line is 1 plus delta 1, the lower part that it reaches is 1 minus delta 1, okay. So it is basically bounded between 1 plus delta 1 and 1 minus delta 1. Now if this is H dash E of j omega, okay, magnitude. Now if I did 1 over 1 plus delta 1, again we are going to do this type of manipulations in today's lecture. If this is the waveform that is given, then 1 over 1 plus delta 1 scaled He of j omega will always be less than or equal to 1 for all values of omega. So the scaling is a very important element in boundedness, but because the filter response you have basically drawn, you can always make sure that there is an upper bound for it to be satisfied. So when you have filters that have got a well defined frequency response, these are bounded transfer functions. So again this is a useful concept, okay. Now of course a subset of this will be bounded real. I will just write it as R, real coefficient. Then there is another set which is lossless. Lossless basically says if I input x of n to this filter H of z and I get an output y of n, the energy is preserved. Summation over n mod yn squared is equal to summation over n mod x n squared. So that means you do not lose energy in the signal. Again, this is a very useful class of filters, a class of transfer functions, and you would call this as lossless. Now you can combine both of them and say there is a class of transfer functions that is lossless, that is real by coefficient, and is also bounded everywhere on the unit circle, and this we said basically points to all pass functions. Okay, all pass functions, this is the class that we are interested in. However, there is another interesting class of filters that we are or transfer function that we are interested in. So this is if you have, for example, h naught of z, I am just going to write a different example from what we considered in the last class, h1 of z, h2 of z, and these satisfied the following condition: magnitude h naught e of j omega magnitude squared plus h1 e of j omega magnitude squared plus h2 e of j omega magnitude squared is equal to 1 or a constant, then this set is said to be power complementary. That means wherever one of them is large, the other ones will have to be small, so that they have to add up to the constant value. And again, this is a very interesting observation that we can make. So power complementary filters, that means if I have this as one of the filters, okay. Now the H1, H2 probably need to be something of this type. Okay. You can visualize this as one combination of power complementary filters. Okay, this is all the way to pi. Okay, so you can visualize them as filters that look like low pass, band pass, and high pass, and so when you square and add them, they add up to a constant. This is a very special class, power complementary class, and of course we are very interested in the case where you have two power complementary functions, because we are looking at the two channel case, because we want to preserve the signal everywhere between 0 and pi, one of the filters being low pass, the other filter being a high pass. Okay, so this is a quick run through of the key elements that we have discussed in the last lecture. Now we will spend the next 10 minutes or so looking at the all pass decomposition. I would definitely encourage you to look up this portion in Vaidyanathan chapter 5. It is presented as a theorem. Theorem meaning it is a result that can be proved. The proof is assumed to have been read. Okay, so we will only summarize the result, because at the end of the day, we will give you enough steps in the proof, but the important thing is how do we take it forward to construct the two channel case. Okay, so here is the statement of the theorem, and I will make it verbatim so you can verify it in Vaidyanathan's book. It is basically exactly stated so that there is no confusion as far as the theorem. Let h naught of z and h1 of z be two nth order. Okay, we are talking about IR transfer functions, so which means that they have numerator and denominator. Once you have taken off all the common terms, pole zero cancellations, what is left is a transfer function for whom we can define the order. Are nth order bounded real transfer functions, BR transfer functions. They are individually bounded real transfer functions. Okay, that means they are well behaved. There is no pole or something that is something that will shoot up on the unit circle. They are bounded. Okay, of the form. Now some of it may seem unintuitive or counterintuitive at the beginning, but just take it down. We will justify the details subsequently. H naught of z is a polynomial p naught of z in the numerator and a denominator d of z. And h1 of z, remember both of them are of the same order. So this one also has got the same denominator, d of z, p1 of z, where the polynomials themselves p0 and p1. So p0 of z is a FIR polynomial of order n. So n equal to 0 to n, that means the highest power of z will be z power minus uppercase n. P 0 comma n subscript 0 representing P 0 polynomial, n is the coefficient index, z power minus n, P 1 of z same structure, n equal to 0 to uppercase n lowercase p 1 comma n z power minus n. D of z is also a polynomial of order n, n is equal to 0 through n d subscript n z power minus n, and under this framework we are going to make the following additional constraints. So, if we further constrain it to be, suppose that P 0 of z represents a symmetric polynomial, which basically means that P 0 comma n is the same as P 0 comma n minus n. So, there is symmetry, it is a finite length polynomial, there is a symmetry that is there, and P 1 of z is antisymmetric. So, which means P 1 comma n will be equal to minus of P of n minus n, 1 comma n minus n. Okay. So, what have we said so far? There are two bounded real transfer functions which are numerator denominator, same denominator, the numerator polynomials, one of them has got symmetry, the other one has got antisymmetry. Okay. Now, if in addition to that you add one more condition, so this was condition number 1, a second condition that if h naught of z and h 1 of z are power complementary, then the all pass decomposition theorem states that we can write down h naught of z as a naught of z plus a 1 of z divided by 2. Notice that this is slightly different from the earlier decomposition where we took the polyphase components to be all these are not polyphase components. Basically, the filter itself is a sum of two all pass functions. H 1 of z is a naught of z minus a 1 of z divided by 2, where the a naught and a 1 are all pass functions, where a naught of z is a all pass transfer function where you have z power minus n naught d naught of z d naught tilde of z, and a 1 of z is z power minus n 1 denominator d 1 of z d 1 tilde of z, okay, where these are causal stable transfer functions. A naught of z, a 1 of z are causal stable real coefficient all pass functions, causal stable real coefficient all pass, and the condition is that the overall order of the filter now comes out to be n naught plus n 1. So, basically what you have done is you have split the nth order transfer function into two transfer functions, one of order n naught and order n 1. They are two all pass functions of those orders, and by combining them you are getting the final structure. Okay. Now, quick checks you can do to confirm that the denominator order is n, because if you take these and you take the common denominator, it will be d naught into d 1. So, order will come out correctly, and then of course you can make arguments about the numerator as well. Okay. Now, this is the theorem. Okay. Now, it is actually not as complex as it sounds. All we are saying is there are two transfer functions which are power complementary, and if I choose the splitting correctly, then I will get these the two factors A0 and A1 to be causal stable all pass functions, and this is exactly what will help us to address this issue, but we are going to basically take away from this whatever we can and learn from this. So here is the interesting parts of it. Again, I am going to give you just the highlights, but please do fill in all of the details. Okay, the first condition that was imposed, that they are both bounded real. Okay, so and that means the polynomials coefficients p0 comma n, that set p1 comma n and d subscript of n, these are all real. Okay, that's the real part of it, and the bounded part comes from h0 e of j omega magnitude less than or equal to 1, h1 e of j omega magnitude less than or equal to 1. Okay, that is the bounded real part. It can be any constant, we have chosen it to be equal to 1. Okay, second condition, that they are power complementary. So which basically says magnitude h0 e of j omega magnitude squared plus h1 e of j omega magnitude squared must be equal to constant. Okay, and now this is not counterintuitive, because they are power complementary and they are bounded, which means that wherever h0 touches the value equal to 1, the other one has to go to 0, only then they can satisfy. So actually it will give you a nice picture if you want to visualize it. If you have a transfer function that is equiripple on both sides, okay. Now the complementary transfer function will be exactly 0 where the other one is equal to 1, this is equal to 1, right, that is the peak value. So wherever that is equal to 1, this, and basically wherever that reaches a minimum, this will reach a maximum, again it will touch 0 like this, and then it crosses over, because in the interim region also they have to add up to equal to 1. Wherever this one hits a 0, this one will reach a maximum, and then subsequently wherever there is. Okay, so this is, so the power complementary property actually gives you a very nice relationship between the two, and one of them being a low pass will force the other one to be a high pass. So this is a very useful property for us to have. By analytic continuation, we say that this is equal to h0 tilde of z, h0 of z plus h1 tilde of z, h1 of z equal to 1. Okay, that is the first step. Now if I can substitute for the expressions for h0 and h1, both of them have got expressions. h0 of z is p0 of z divided by d of z, h1 of z is p1 of z divided by d of z. Substitute into this, we get a very useful form, which is p0 tilde of z times p0 of z plus p1 tilde of z p1 of z, okay, and this is equal to d tilde of z d of z. Basically I have cross multiply. Okay. Now comes some interesting observations as to why some of those results or conditions were imposed. P0 tilde of z. Okay, so now I want you to sort of visualize. Let me just write it on the side. If P0 of z can be written in the following form: P0 comma 0, P0 comma 1 z inverse, P0 comma 2 z minus 2 dot dot dot. Because of the symmetry conditions, the last term will be P0 comma 0 z power minus n, the one before that will be P0 comma 1 z power n minus 1. So that will be the relationship. So now if I do P0 tilde of z, what do I have to do? I have to do the conjugation, does not make any change, these are all real coefficients, and I have to replace z with z power minus n. Okay. Now, easy to verify that if I do that, then what will happen, I will get this polynomial with all powers of z. If I pull out z power n, I will get back p naught of z because of the symmetry. So, p0 tilde of z is nothing but z power n times p0 of z. That is a very useful result based on the symmetry that we have enforced. Similarly, p1 tilde of z is equal to same type of relationship, but now there is a minus sign because of the anti-symmetry. So, this can be written as minus z power n p1 of z. Okay. So, we now say that equation 1 becomes, with these two substitutions, it becomes p naught squared of z. There is a z power n sitting outside, p naught squared minus p1 squared of z equal to d tilde of z d of z. A nice form is p naught squared of z minus p1 squared of z, taking the z power n to the other side, z power minus n d tilde of z, that is a nice form because that makes it causal, d of z. Okay. And left hand side, of course, you can factorize it into p naught of z minus plus p1 of z into p naught of z minus p1 of z. Okay. So, some interesting observations which we will utilize and then quickly move forward into the key, the crux of the reason for this. Keep in mind that what we are doing is giving us some tools for us to develop the results. So, in addition to the mathematics, the tools that are being used are very important. Now, the zeros that are captured by p naught plus p1 and p naught minus p1 are the zeros of d of z and d tilde of z. So, basically whatever are the zeros and its reciprocal conjugates are going to be captured. Okay. Now, there is yet another interesting flavor to this particular discussion. Let me just add that also here. P naught of z minus p1 of z, if you use the results that are that we obtained just a few lines earlier, remember these results. If you use that, then this is equal to z power minus n p naught tilde of z plus p1 tilde of z, even better. Okay. So, basically p naught plus p1 will capture some set of zeros, the reciprocal conjugate zeros will get captured by p naught tilde of z plus p1 tilde of z. Now, again this is a very important element. Another observation which is useful for us. Okay, here it is, p naught of z plus p1 of z. This is a real coefficient polynomial, right? That is what we have assumed. These are p naught and p1 are real coefficient. So, that means if there is a 0 at z naught, there must be a 0 at z naught star, z naught conjugate. So, these zeros cannot occur individually except if they are on the unit circle, on the real axis. Anything that is not on the real axis must occur as a conjugate pair. Okay. Now, if you now say that z power minus n p naught of z tilde plus p1 tilde of z, if I look at this, that basically says that wherever there is a 0, the reciprocal conjugate also has to be present. So, this will be a 0 at 1 over 0 z0 conjugate, this will give me a 0 at 1 over z naught, because okay. So, effectively between the two of them you will get Z0, Z0 star 1 over Z0, 1 over Z0 star. Or in other words, you could make the following statement. Okay. If you treat this as one entity, if you treat this as one entity and this as the other entity, you can make a statement which says that the zeros of these two will be disjoint. They will, one will have the set of zeros and the other will have the reciprocal zeros. Now the question will be is, how do you know that they are disjoint? What happens if they are on the unit circle? Then the reciprocal will also be on the unit circle. Now what is the assumption on P of on H of Z? Stable. So which means that you cannot have a 0 on the unit circle. So zeros of D of Z must be strictly inside the unit circle. Zeros of D tilde of Z will be strictly outside the unit circle. Okay. So and also keep in mind that so between D of Z and D tilde of Z you have 2n zeros. That will also have to be captured by these two subsets in our discussion. Okay. Is what we have said so far, is it reasonably clear? Okay. Now deliberately I am going to leave this and ask you to think about another topic that you have already studied in DSP, but it is very useful for us to revisit at this point. Okay. Now supposing I have a FIR filter H of Z. Now it has got a finite number of zeros. So supposing it is of order n. It has got n zeros. Now some of the zeros are inside the unit circle, some of the zeros are outside the unit circle, and no zeros on the unit circle. This is the assumption that we are making. No zeros on the unit circle. Now this is an aside. Maybe you want to write this on a new sheet of paper so that you can continue the earlier discussion subsequently. But for now this is a useful observation on the no zeros on the unit circle. Okay. So now if I group the zeros that are inside the unit circle, which I will call as A of Z. So and there are, let us say, n naught zeros inside the unit circle, inside mod Z equal to 1, multiplied by B of Z, which captures the zeros that are outside the unit circle, and this says there are n1 zeros outside mod Z equal to 1. Okay, and of course n naught plus n1 must be equal to uppercase n, total number of zeros that are present. Okay, so here is the key statement which I hope will remind you of a result that you have seen previously. I can always write H of Z in the following manner: A of Z, instead of B of Z I am going to write the paraconjugate. So paraconjugate means I must write Z power minus n1 B tilde of Z. Now if B of Z has zeros outside the unit circle, the paraconjugate will have zeros inside the unit circle. So which means that this whole setup has got zeros inside the unit circle. Zeros inside unit circle. How many zeros? N. You have got n zeros inside the unit circle. So this actually is a minimum phase polynomial of order n. Okay, so this combination is actually a minimum phase polynomial of order n. In fact, we could write it as H min of Z. Why can I write it as H min of Z? It has got the same magnitude response as H of Z, but it has got all the zeros inside the unit circle. Am I correct in making that statement? Because the paraconjugation gives you on the unit circle, it gives you the conjugate response. Yeah.
So this won't be equal to H of Z.
Yes, I haven't finished that. Yeah. So I would have to now write the remaining part, which would be B of Z divided by Z power minus n1 B tilde of Z. correct. Now this is an all pass. Is it stable? The zeros of B of Z are outside the unit circle. The paraconjugate will have zeros inside the unit circle. So therefore this is a stable all pass. This is a stable all pass, and all pass means magnitude equal to 1. So this is HAP of Z. So this is where the statement comes from, where we say that any FIR transfer function can be written as H min of Z times HAP of Z, where HAP is a stable all pass transfer function. This factorization I am sure you would have encountered, and this is a very useful form, because if suddenly someone says I want to have a minimum phase filter, you can actually very easily do it by reflecting the zeros inside the unit circle. The magnitude response will not change, but you would have affected the phase response, because the all pass function has got a phase response but no magnitude response. So again, it is a useful result, but it plays an important role in what we have to do in the discussion now. Okay, now what are the things that we are, what has this sort of corollary or result has shown is, when you think of polynomials, think of zeros inside, zeros outside, and always keep in mind that this the paraconjugation flips the location of the zeros. Keep that picture in mind, very useful for us, and we will now, next few lines, so now we go back to picking up from where we left off. Okay, so where did we leave off? We said that the power complementary constraint can be written as P naught of Z plus P1 of Z, okay, and Z power minus n P naught tilde of Z plus P1 tilde of Z. This is equal to the expression that we have, Z power minus n d tilde of Z d of Z. Okay, did we get that correctly? I think so. Okay, if I did make a mistake, just catch me on that. Okay, so now let us look at the polynomial P naught of Z plus P1 of Z. Okay, now we do not know where the zeros lie, it is a combination of two polynomials. So let n1 zeros of P naught of Z plus P1 of Z be inside the unit circle, okay, and the others are outside the unit circle. How can I make that statement? Why not on the unit circle? Because what is there on the left hand side must be on the right hand side, and the right hand side does not have any zeros on the unit circle. It has to be either inside or outside. Okay. So we will call this factor as D1. So D1 of Z is a polynomial of order n1. Polynomial of order n1. Okay. So where will these zeros come from? D1, that will be a subset of D of Z, because D of Z has got zeros inside the unit circle. Some subset of it got captured by P naught plus P1. Now P naught plus P1 has got some zeros outside the unit circle. How many zeros outside the unit circle? Basically it has got n naught equal to n minus n1 zeros outside the unit circle. Zeros of P naught of Z plus P1 of Z are outside unit circle, are outside the unit circle. Okay. So basically these will have to be factors of d tilde of Z. Okay. So let us call this as d0 tilde of Z. Basically these are factors from there. So in other words, because it is is order n0, if I want to make this causal, this must be Z power minus n naught. So then I can write an expression for P naught of Z plus P1 of Z. Okay. Now this is equal to some proportionality constant alpha times d1 of z, z power minus n naught d naught tilde of z. Okay. Zeros outside the unit circle, they have to be part of d tilde. So, I am using the notation d naught tilde to be some factor of d tilde of z, and so this is a useful form for us. Okay. So, d1 of z is a polynomial of order n1, polynomial of order n1, d0 is a polynomial of order n0 which is equal to n minus n1. Okay. So, now what we do is basically what we have done is we have said d of z got split into two parts which one of which we called it as d1, another one which called it as d naught. So, if I now visualize it as d of z as d naught of z times d1 of z, z power minus n d tilde of z is d naught tilde of z, which will be z power minus n naught, then z power minus n1 times d1 tilde of z. If I multiply the two together, z power minus n d tilde of z times d of z, then what I will get is z power minus n naught, z power minus n1 will add up to z power minus n d naught of z, d naught tilde of z, d1 of z, d1 tilde of z. Okay, I have just done the factorizations. Okay, hopefully there is nothing confusing, everything is straightforward, just go through. So, keep this expression in a visible place. Now, what about p naught of z minus p1 of z? It must contain all of the zeros that are reciprocals of p naught of z plus p1 of z, right. We because this is equal to, we showed the expressions that z power minus n p naught tilde of z plus p1 tilde of z. Okay. So, p naught plus p1, you can take a tilde of the entire expression. So, this will be equal to alpha times z power minus n, whatever was there in the expression for p naught of z plus p1 of z, you have to take the conjugate of that. So, this will become z power n naught, because you are now, what we are doing is replacing z with minus z, and this one becomes, previously we had d naught tilde. So, now what we get is d naught of z, previously you had d1 of z, now it will become d1 tilde of z. So, basically this would be the, so combining these two, you find that what we get is alpha d naught of z, z power minus n1 d1 tilde of z, very nice. Okay, that is a nice expression that we have been able to get. Okay. So, this is an expression that we have been able to get. Now, if you also look at this following expression, p naught of z plus p1 of z, we said that this is equal to, this is a factor, this is equal to alpha times d1 of z d naught tilde of z. Then the second term here is p1, no, p naught of z minus p1 of z. This is equal to z power minus n d of z d tilde of z. So, which basically can be written in the following way: d naught of z d naught tilde of z, d1 of z d1 tilde of z. right. So, from this you get another expression for P naught, P naught of z minus P1 of z. Okay. So, this will have, take this to the other side, you will have 1 over alpha, basically take off the, did I make any mistake? If I have made any mistake, just let me know so that I do not get, z power minus n naught is also there. Okay. So, there is a z power minus n naught. So, take it to the other side, what you will be left with is d naught of z, z power minus n1, z power minus n1 d1 tilde of z. Okay. So, basically we got two expressions, let me call that as A and B, both are valid because what did we say, P naught of z minus P1 of z, we used the direct expression, we also looked at the overall expression and obtained it. If you look at these two, A and B will tell us that alpha squared must be equal to 1 or alpha equal to plus or minus 1. So, but for this plus minus 1 scale factor, the expressions are correct. Okay. So, here is the crucial step, combine the results that we have so far, h naught of z plus h1 of z, this is given by P naught of z plus P1 of z divided by d of z. So, P naught of z plus P1 of z, we already have an expression for that, it is z power minus n naught, I am going to take alpha equal to plus 1, d1 of z d naught tilde of z, denominator z power, it is actually d of z. So, d of z can be written as d1 of z into d of z. Okay. So, this can be written as d1 of z into d naught of z, that is the denominator. I am to cancel d1 present in the numerator and denominator, this is z power minus n naught d naught tilde of z divided by d naught of z. Okay. D naught of z. Okay. Likewise, please verify that h naught of z, this is an all pass. This is an all pass function. Okay. Now, h naught of z minus h1 of z, h naught of z minus h1 of z can also be verified, and you can show the following, and you can show that this is equal to z power minus n1 d1 tilde of z by d1 of z, which is also an all pass function. Okay. So, h naught plus h1 can actually be implemented in the following: scale factor of 1/2, all pass function a naught of z, all pass function a1 of z, a crisscross, the upper branch goes with a plus 1, lower branch comes with a minus 1, the overall transfer function will be the two filters that we are interested in, h naught and h1. Okay, so, if this is x of n, this is y naught of n, which is x of n filtered by h naught of z, filtered via h naught of z, and the other one will be the filtered by H1 of n. Okay, so what is it that we carry forward from here? That if I enforce the polyphase components, so let us go back to the theorem. If I enforce the symmetry, enforce the power complementary property, and with the appropriate order, then we can get the transfer functions to the H naught and H1 to be a sum and difference of all pass functions. Okay. So this is a useful result in the context that we have been able to develop a couple of interesting concepts where we talk about separation of zeros inside the unit circle, outside the unit circle, and then the factorization, and then how to get the results from there. Okay, any questions on the all pass decomposition that we have developed? All pass decomposition part that okay.
So
Now are these, pardon?
the symmetry
The symmetry basically comes in this part. The symmetry and the anti-symmetry. That is where that's what helps us do the factorization. Otherwise, you would have gotten H naught squared plus H1 squared. When you get them as differences, then you can then get the sum and difference of the. Okay. Now, are these stable all passes? Are they stable all pass functions? Yes, because both of them have got factors of d, and d is stable. All zeros in all the zeros of that polynomial are inside the unit circle. So therefore, everything is stable. Everything hangs together. This is a interesting result, a very nice result. Okay, but more important, what did we get out of it? All the tools. Keep that in your mind. Manideep, anything you want to announce? Okay. So okay, so now we move on to the next topic in the that is the mth band filter and the Nyquist filters. Okay. Now we said the following, that if I were to do a Nyquist filter, okay, I am looking at the Nyquist portion of it, the Nyquist filter. We said that we could write the filter in the following form: h of z as some constant 1, because the one of the polyphase components has got only one coefficient, plus z inverse times E1 z power m plus z minus 2 E2 z power m dot plus z power minus m minus 1 E m minus 1 z power m. Okay. Now here is a task for you to do. What does this structure of the interpolation filter tell you? That there are 0 crossings of the impulse response, correct? So when I convolve, when I do the interpolation, initially I have 0 valued samples, some number of them. These are my input samples. When I do the convolution with this filter, what happens is these 0 values get filled in, but the original coefficients do not get modified. Notice the green ones remain in the same value, they do not get modified. So for example, this is how this interpolation will fill in these values, but those 0 valued, and that is a very important result. So if the green was the input signal, x of n went in, got upsampled by a factor of m, and then you did the interpolation filter, then you get the complete signal. Okay. Now let me call this as the interpolation filter h of z, after which you get the composite signal which is y of n with the 0 valued samples. Now, if I take y of n and downsample it by m, will I get back x of n? If the interpolation filter had been a Nyquist filter, then the input has to, because you didn't touch the, you didn't modify the those coefficients. Remember, it is a zero phase filter, so there is no shifting of the signals happening. Okay, so this is actually true. There is no question mark. You will actually get this. Okay, now can you show what you know from intuition and through the verification, graphical verification, you have shown this. So, can you show that y of z is equal to h of z times x of z power m, right? That is the equation that is left for us. Can you show that y of mn is equal to y of n? It is a slightly non-trivial exercise, but once you see the trick, you will see that it is fairly straightforward. I do not want you to use the graphical argument. I want you to use a mathematical framework to because now the y of mn basically means that y of z. So basically, let me call this as y dash of n. So y dash of z is 1 over m summation k equal to 0 through m minus 1 y of z power 1 by m w m k, right? You have to do that. Now go in and substitute and show that this hangs together. So assuming that you have done that exercise, I want you to pay attention to this result. H of z, which is the filter that we have shown here, the filter of that form. Can you tell me what happens if I add shifted versions of this filter? K equal to 0 to m minus 1 h of z w m k. Okay, what is h of z w m k? If h naught of z was a low pass filter, this will be shifted by 2 pi over m. 2 pi over m, this is h of zw, if this was h of z. Okay, and now if you take all the shifted versions, remember h of z will have to be a low pass filter with cutoff pi over m, right, plus minus pi over m. So if I shift all of them, they will cover the entire range 0 to pi, 0 to 2 pi. But I want you to see what happens. So basically, when you, this is the first will be h of z plus h of zw plus, I am going to just write it in this form just for ease of wm m minus 1. Okay. So basically, this is the summation that we are trying to do. H of z is what? 1 plus z inverse E1 of z power m, sorry, E1 z power m plus dot 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 plus z power minus m minus 1 E m minus 1 z power m. H of zw, that means wherever there is z, replace with zw, this one will become 1 plus z inverse w inverse E1 z power m remains as E1 z power m, because w raised to the power m. So this is this remains as z power m. Likewise, this becomes z power m minus 1 w minus m minus 1 E m minus 1 z power m. Okay. Now please go through and write down the expression for the last one, 1 plus z inverse w minus m minus 1 E1 z power m plus dot dot dot. I will just take the first equation, and so I have to add all of these. if I add this vector, I get m, because all of them are plus 1s, all of them are plus 1s. Now, if I add the next column, notice I have E1 z power m z inverse as common, and then what I will have inside. So, this can be written as z inverse E1 z power m multiplied by 1 plus w inverse w minus 2 plus w minus m minus 1, powers of the roots of unity. So, therefore, this is equal to 0. So, similarly you can so this adds up to 0. Similarly, each one of these columns you can verify adds up to 0. So, basically what we said was this expression for a Nyquist filter will add up to m, or in other words, a Nyquist filter also satisfies the following condition, that 1 over m summation k equal to 0 to m minus 1 h of z w k must be equal to 1. Okay. This is what we refer to as the mth band property. Any filter that satisfies this condition is called an mth band filter. Now, does an mth band filter always have to be a Nyquist filter? No, need not be. It just so happens that the Nyquist filter satisfies this property. So, from the Nyquist filter we derived a certain property which is a very interesting property, which we then say, okay, this is something that we would definitely want to keep in mind in our toolkit. Now, the case when m equal to 2, can you write down the expression for me? This is h of z plus h of minus z add up to 1/2, scale factor of 1/2 must be equal to 1. So, this is the condition of a half band filter, Okay. Now, that means the a half band filter, when you factorize it for a half band filter, you will get the following form. It will be equal to 1 plus z inverse E1 of z squared, which is of course, take the mth band case, your polynomials, you are dividing this. Now, I want to ask you if this is intuitive, that this is what will happen, and answer is, well, it is actually fairly straightforward, because the Nyquist filter, when I want to do upsampling by a factor of 2, will give me a non-zero value which is equal to 1, then the next sample will be 0, then I will get a non-zero, well, wait a minute, no, every second sample will be 0. So, there will be a non-zero value next, there is a non-zero value, and then it crosses 0, non-zero value crosses 0, non-zero value crosses 0. So, this is how a Nyquist filter with pi by 2 as the cutoff will look like, because every second coefficient will turn out to be 0. So, now if I do the polyphase decomposition on both sides, this is a symmetric filter. Notice that you will get one coefficient of 1 and then all zeros elsewhere. So, this would be the repeating structure. So, this actually validates this particular form. Okay. So, the first zeroth order polyphase component is equal to 0. So, now may ask you a question, may seem a little bit trivial. What can be the order of a half band filter? Order of a half band filter. Again, it all hangs together. So, so there is a 0 valued coefficient, if I want to look at the non-zero value, supposing I want to take up to the second non-zero term, what will be the, it is some odd number, because I can always leave out the last one. So the number of, so the length of a half band filter is going to be 1 plus some odd number of terms. So I will call it as 2j plus 1, and there will be a symmetric one on the other side. So the total length will be 1 plus 2 times 2j plus 1. Why 2j plus 1? Because it has to be an odd order, or odd number of samples, because I can either get 3 samples or 5 or 7 or 9 likewise in a half band filter. I am only talking about a half band filter. So which means that the length is given by 4j plus 3, that is the length of the filter. Okay. If this is the length of a half band filter, the order is always 1 less than, when I assuming that I have shifted them all to make them causal, the order will be 4j plus 2, 4j plus 2. Okay, which means it is even but not multiple of 4, even but not multiple of 4. An interesting observation, interesting filter, interesting results, but still not quite sure where this is going to take us and how we are going to work with the whole thing. Let me just end with one last result for today. Again, this is a very straightforward result. Once we have this in place, we will be able to finish the discussion in the next class. Okay, so let us take a mth band filter. Mth band filter. Mth band filter basically says that we have the following condition: 1 over m k equal to 0 to m minus 1, h naught of z w k equal to 1, equal to a constant. Okay. So h naught of z is the mth band filter. The property that it satisfies is that the sum of the shifted versions scaled by 1 over m is a constant. Now I would like to write down the DFT filter bank, DFT filter bank, okay, which is basically h naught of z, h1 of z, which is equal to h naught of zw, and last one is h m minus 1 of z equal to h naught of zw m minus 1. Okay, so this is the DFT filter bank. In terms of the polyphase components, basically I would now have the polyphase components as E naught of z power m plus z inverse E1 z power m. E naught of z power m will be a constant, but for now I am just writing it in its full form, z power m minus 1 E m minus 1 of z power m. Okay. Now please verify, I think we may have already written this, but in case we have not, this can be written as the DFT matrix times a diagonal matrix which is 1 z inverse z minus 2 dot 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 z power m minus 1 times E naught of Zm, E1 of Zm, Em minus 1 of Zm. Okay. Now here is a very important result. If you want the vector h, if this is the vector h, it has got m minus 1 m filters. If this vector is supposed, it should be power complementary. What does that mean? h of z, that tilde paraconjugate, times h of z, because this is the same as saying this is summation k equal to 0 to m minus 1 mod h k e of j omega magnitude squared when you equate it on the unit circle, right. That is power complementary. But if I want to write it in the in a general form, the power complementary property should be enforced in this following fashion. This should be equal to a constant, that should be equal to a constant. Okay. Now, what condition does that impose on the polyphase components? If you just substitute the fact that h can be written as w times delta, which is the diagonal of times the vector e. Now, h tilde times h, I am just dropping the z's for now, this can be written as e tilde okay. Now, this is delta tilde w tilde, but w is only the matrix, it is a constant matrix. So, basically there is no powers of z, so it will become the conjugate times w delta e. Notice that these two will cancel each other, this will be powers of z, this will be powers of z inverse, they will cancel each other, leaving you with e tilde e. Okay. So, there is an important result, I will give you in a minute. H is power complementary if and only if E of z is power complementary. E of z is power complementary. Now, this result actually comes into play in some in a intricate way in understanding the M channel case, not the 2 channel case. But what is very important for us is the last result that I will write down before we end today. There was a question?
So it should be IDFT matrix, right? Instead of W, it should be.
Did I?
It should be W to the power minus.
Okay. Okay. So maybe this one should be W inverse tilde. Okay. Yeah, I'll have to verify because I think you're right, because what you will get is the negative powers of W, which is the IDFT matrix, correct. Yeah, it's you're absolutely correct. Yeah. Okay, so the relationship between H and the polyphase components is an important one. Okay. Now, I just want you to look at one more element before we close today's discussion, because this is also useful, an important result for us. So, what did we write down? Summation over k hk tilde of z, hk of z must be equal to a constant. Okay, and we have the relationship that hk of z is nothing but h0 of zw raised to the power k. These are all shifted versions of the filter. Now, a very important observation. So, the first term in this summation, will be h0 tilde of z, h1 tilde of z, h0 of z. Let me call this as G0 of z. Okay. So, basically h0 tilde h0, I have called it as G0. So, this is the power complementary constraint. Now, rewrite the power complementary constraint with G0. It will come out to be summation k G0 ZWK, k equal to 0 through m minus 1. Am I correct? Okay. So, what does that make G 0? This has to be equal to a constant. So, this means G 0 of Z must be a mth band filter, mth band filter. Okay. Now, how do you get an mth band, how do you get a power complementary set of functions, m functions that are power complementary? Trivial. You design an mth band filter, you have to do this. So, G 0 equal to h naught of tilde h naught. Now, what can you tell me about the zeros of h naught and h naught of tilde? They are reciprocals of each other. They are no overlapping this, unless it is zeros on the unit circle. Okay. So, what do you have to do? You have to take G 0, take its zeros and map them into either h naught or h naught tilde. That process is called spectral factorization. Okay. And you may have come across this in control systems. We do that when we want to have a certain design constraint on our filter. This is called spectral factorization. So, design an mth band filter, take a spectral factor, I will give you a set of power complementary functions, because all the DFT shifted versions are power complementary. Now, mth band filter has got a very unique property, that its polyphase component, one of them is a constant and other things. Okay. But a very interesting interplay seems to be present between the following conditions: power complementarity, mth band property and spectral factorization. Okay. So, there is a very interesting interplay of these three elements. So, now I want to ask you, I want to get only two power complementary filters. I want you to design for me two power complementary filters. What will you tell me? Take a half band filter, take its spectral factor, and that will give you power complementary property. Okay. I hope it is pointing you in the direction of how do we get perfect reconstruction. We will answer that in the next class. The question is, if I have mth band filter, satisfies the mth band property, and in this particular case what we have shown is that now maybe the question, if I rephrase your question, the question is, can I always factorize an mth band filter as a polynomial and its paraconjugate? That is a very important question, because this is possible only if I look at G 0 of Z on the unit circle, it must be of the form something magnitude squared. As long as I have if it satisfies that, then magnitude squared can always be factorized as polynomial and paraconjugate. No issues with that. So, I would come about to answer your question, I would answer the question, I mean I would say that when can you always guarantee that G 0 of Z can be factorized in this form? It is when this condition is satisfied, right. Now, again a very important follow on question is, take the half band filter. Half band filter we showed, we sketched it here, H E of j omega need not be if I plot this response, it could be something that does this, right. It can have positive and negative values. How do I ensure that this is spectral factorizable? If this is delta 2, right, it oscillates between plus delta 2 and minus delta 2, plus delta 2 and minus delta 2. If the filter H E of j omega, if it is a linear phase filter, e power minus j omega n by 2 H r E of j omega, this is real valued. If I add delta 2 to this, what will happen? It will shift the response to be strictly positive, greater than or equal to 0. Okay. It does a very important thing. If I take the magnitude of this, what will it look like? The magnitude response, it will look like this, am I right? Notice where are the zeros? They are here and here. If I, that means they are at here and here. Now when I keep shifting this response higher, what will happen? These two zeros will come and merge. So what happens in this case, if I shift this by delta 2, I will get a response that does not have these sharp edges, but has smooth values, and these turn out to be double zeros because those two zeros actually merged into one. So these become double zeros, okay. So you must have double zeros, only then you can factor them. If it was a single zero, then there is no way I can factor them. And remember, the zeros of H naught and zeros of H naught tilde must be reciprocal of each other, right. So that also has to be satisfied. So spectral factorization. So the next lecture I will begin by saying, when I have something of the form of magnitude squared, okay, what is the structure of the zeros? You will find that the zeros and have a very specific structure, and that lends itself to spectral factorization. So basically G0, which is a half band filter, if you design it, shift it up so that all zeros become double zeros, then you are permitted to do a spectral factorization of this form, where you can actually satisfy the half band property and the power complementary property. Okay, we will pick it up from here at the next class. Thank you.